Welcome to Study Loop.
And so this question, we have a signal that is reflected from a plane, and the question asks us how the reflected signal will interfere with the original signal. So this question, it would be much more helpful with a graph, but since it does not have the graph, we will have to assume the configuration of it. So there are two ways of thinking about this problem. One is, say, if this is a station and then this is a plane that is right above it, you have a plane wave signal. So one arrived at the station, another one hits the plane and reflects over here. So this height of the plane is the total distance. It's the total path difference between these two, between the top signal and the bottom signal. And another way of thinking about it is to think if the station is very far away, and then one light arrives here, another light goes up here and goes down. So the problem about this is that the path difference is not just this h. You will have more path difference when you have this line instead of the horizontal line. But so a lot of people I encountered have confusion because they were thinking about the second configuration. But the problem is, if you read the question again, it says from a distant station. So when this distance is infinitely large, this little bit height, does not really matter. You will think that these two paths, they're not that different, and you can consider them as almost identical. So that's why in this question, you really should think that this h, you only have one h to consider. H is a path difference between the reflected wave and the wave that goes to the station directly. So that's just a little bit clarification that I have to make before I get to part A. So okay, now let's get to part A. We are given the frequency of the television signal. So television signals are radio waves. Radio waves are EM waves, so they travel at the speed of light. We have this formula that the wavelength equals velocity of frequency. And if that does not make much sense to you, just remember frequency is a reciprocal of time. So this is the same so V over F is the same as V times period. So this is the same equation as saying distance equals velocity times time. So V here equals, it's a velocity of light, 10 to the 3 times 10 to the 8th meters per second, over 75 times 10 to the 6 hertz. This gives us 4 meters. So that is a wavelength we have. So what is 122 meters in terms of lambda? We want to calculate the phase shift. And to calculate the phase shift, we want to know the distance d over lambda. That is how many wavelengths we have in this whole in this distance. And then we type it by 2 pi, because for a wavelength it corresponds to a phase shift of 2 pi. And then we say assume it change in phase upon reflection. That means when the wave is reflected from the airplane, it experiences a phase shift of pi. Okay, so that now we plug in the numbers. 122 meters minus 4 meter divided by 4 meter times 2 pi plus pi equals 122 over 4 is 30.5, and then times 2, and so that is a total of 62 pi, which is 30 times 2 pi. So that means we we can think of it as a total of 31 lambda is in the phase difference. And because it's an integer times 2 pi, what it means is that constructive interference will occur. So constructive. So by having that airplane at 122 meters above the station, you actually get a stronger signal because of the constructive interference. Now it asks what kind of interference will occur if the plane is 22 meters closer to the receiver. So it's the same formula except that now we have d is 122 minus 22. So the new distance we have is 100 meters. Now we have 51 pi, which is 25.5 times 2 pi. So now we do not have an integer, we have a half integer. And what that means in phase difference is if we have a half integer times 2 pi, then the interference is destructive. So if the plane happens to be a little bit lower, the television signal we get will actually be a lot weaker.